All right, good afternoon, everybody. All right, so what we're going to do today is we are going to complete our discussion of hash tables. And then after that, we are going to go into an idea known as a maximum heap. And this is where we're going to start kind of making our transition from hash tables to what we're eventually going to study beginning in the second half of the semester, known as binary search tree. So we got to mute everybody here. Mute all. No. Okay, so please follow the directions that are up there. You should be downloading several files. And then what I want you to do, once you get on that page, I want you to take the first 3 minutes of lecture and attempt problems 1 and 2. They are linear probing problems. And the whole idea is that you're going to have a hash size, and you're going to hash a certain number of keys into a particular hash using your knowledge of hash functions. So we'll go over that, and then what we're going to do after that is discuss this idea of rehashing. What happens when we get too many elements into a hash? How do we rebuild the hash? And then after that, what we're going to do is we're going to talk about something called lazy deletion in hashing. Why we can't just delete an element from a hash like we might do in a dynamic array or a linked list, and how we get around this. So please take the next 3 minutes to work on these problems. And again, I have all the Slack up, so you're welcome to ask questions and exchange ideas on the Slack during lecture. And those of you who are just coming in, it's this link, lecture 11 in class. So you're creating it at the folder at the same level, and once you do it correctly and do that ls star, it should look like this. And then when you do make problem 1, it will generate this particular problem, and it'll ask you to put in the buckets. Okay, so does anybody have the answer to problem 1? You can either share it by speaking up, or you can state what you got for the answer in the Slack. Anybody? Yes. Okay, so you have 0, 19. Oh, bucket 0 is 19. Okay, so I'll just put those, do the, all right, so there's the solution. So bucket 0 is 19. Pretend that you don't see that there. So bucket 1 is 0. Right. So this is going to mark me wrong because I put in 245, but it's going to be 19, 0, 0, 0, 25, 47, and 82. And the reason we got that is because in the initial hashing, what's going to happen, we have 25, 47, 82, and 19. And we're going to have buckets 0 through 6. And 25, so it's everything mod 7. So 25 is going to end up in 4 because 25 mod 7 is 4. Then we're going to get 47. And 47 is 5. Then we're going to get 82. And that's going to be 6. And then what's going to happen is 19 mod 7 is going to be 5. So with the linear probe, it would try to go here. It's not going to work. Adds 1, tries to go here. That's not going to work. So it's going to put it up there. So that's why we get 19. And then for simplicity, in the write-up, I ask you to put 3 zeros there. Okay, so I would like somebody else, either in the Slack. Okay, so I saw there was one question response in the Slack. Let me do make prob 2. And so here we have 9, 41, 14, and 20. And it's going to be the same thing. We get 0, 1, 2, 3, 4, 5, and 6. So where are we initially going to hash 9? Yes, in the back. 2, very good. So 9 will be here. So what about 41? Yes. 6, very good. 14? What's 14 divided by 7 with what's the remainder? Yes. Very good. 14 mod 7 is 0. So now what's going to happen with 20? Where does that end up? Yes. What's that? Ends up in 1. Very good. So the reason why we tried hashing it to 6, that didn't work. 0 already had something there. So that's going to be 14. And so if I put up this one, that would be 14, 20, 9, 0, 0, 0, and the other one was 41. And we see that that's the correct answer. And if you have them both there, you'll see prob 1 and prob 2 text. So good job, everybody. All right, so now we're going to start discussing this idea of, well, what happens when we have too much? So we've talked initially about linear probing, and then you all solved that problem. And that works really well if we get fewer than the number of buckets. But what happens when we reach a point where we want to have more than 7 in an unordered map, and we want to be able to store all these elements yet still gain that big O of 1 improvement? So what's going to happen is that once you, in a linear probe hash, once you start getting over 50% of the size, you're now getting a significant increase in the amount of collisions that you're going to get. So what we will do is we will learn that we're going to rehash, which we're going to do is we're going to double and find the next we're going to find the next largest prime number and start storing elements in the bucket that way. So for example, here we have 7. If we work through the problem that we did in the last lecture, we initially have 76, then 93, then 40, then 47. And so now what's going to happen is we're starting to get filled. We're going to start getting a lot more collisions. So what's going to happen is I am going to rehash by creating another hash table. So we're making a copy. And then I'm going to start going through in order 47, 93, 40, and 76 by iterating through the underlying dynamic array. That allows me to copy those values and rehash to the new location. And then, now that I have a new hash, I delete the old dynamic array off of the heap. We preserve memory. Want to be efficient with how we allocate memory. And then what we're going to do is then we start hashing in elements. And so at this point, once I do 55, we'd have to rehash again. So for those of you who took the lab yesterday, you saw that in the first problem, the way I got around that excessive rehashing was to put in 2 times the value, and then we actually printed out the number of buckets, and you saw that it was 2 times the value, and it was the next largest prime number, just like we've designed in our hash table. And so what we're going to do with this rehash is we're going to take a similar approach to see if we can reduce the number of collisions. So does everybody understand kind of the general gist of what the procedure is? So what happens is there is a worst case scenario where we have a big O of n insert. And it's amortized down to big O of 1 because most of our inserts use the key and value and have a good lookup. On Thursday, we're actually going to go over a process known as quadratic probing, and then Robin Hood hashing, and then cuckoo hashing, where we're actually going to use mathematical approaches to reduce the number of collisions in a hash. For now, we're going to study this idea of rehashing. So what I would like you to do is I would like you to go to linear probe 6.h, and that's in the include folder. So you would go here. So you go to include, and you go to linear probe 6, and if memory serves, I believe we're going to start at line 125. So we go down here. Yes, you should see this rehash with a bunch of comments. And we're going to walk through the process of coding this up to do the exact same thing that I just showed you in the animation. So the first thing we're going to do is we're going to take advantage of the C++ standard template library. We also wrote the same thing when we did a dynamic array, when we wrote our assignment operator. So this is a good example of why it is we want to write an assignment operator and a copy constructor for our classes when we have an underlying pointer to a location of memory on the data heap. So the first thing I would like you to do is I'd like you to write standard vector. And if you remember, we had a struct called hash entry that's going to keep track of all of our elements. So we're going to have hash entry as the templated type, and we're going to call this old array. And we're going to set that equal to the current array. So what I do is I have a copy, and I'm going to iterate through that array, and we're going to hash all of the elements into a new array. But in order to get the new array, I need to actually clear out the old array. And the method in the C++ library that allows me to do that is array.clear. So let me zoom in a little bit so everybody can see array clear like so. And so now we have a copy of the old hash. We have cleaned out the new hash. And now we're going to start hashing in elements. And we have to actually create that size. So we're going to resize the array. And now that it's clear, here's how this is going to work, and here's how we can use this in the C++ STL. We're going to call a method called resize. So clear got rid of all the locations, because when we have a new hash table with a new number of buckets, it's going to hash to new locations. So we're going to call this resize method. And the resize method, we are going to get next prime, where we wrote this function next prime that gets the next largest prime. And I'm going to say old array dot size plus 1. And I need another parentheses there to make sure that we have everything lined up. So now I'm getting the next largest prime number. And that's what's the new array. It has nothing in it, but it's now a larger prime number. And this will allow us to be able to ensure that when we have a distribution of keys that is not uniform, for example, for those of you taking logic design or computer architecture, byte addressing will go to addresses of 8 that are multiples of 8. So therefore, we use prime number to ensure those distributions of non-distribution inputs. So now what we're going to do is I'm going to set num hash equal to 0. So now we're going to rehash everything. And that allows us to keep track of the number of elements in the hash. And so one way we can do this, in the Coding Challenge 5, I talk about this new way of doing iteration, right? So we're iterating through the array, and the array is hash entry. So we can do hash entry, and I'll call it cur for old array, right? And so that's iterating through the entire old array. And then down here at the bottom, I am going to put a new bracket to close the for array. So it iterates through the entire thing. And now what we have to do is we have to check to see if if cur state is active. So if you remember, I'm going to scroll up really quick just to refresh your memory. We created an enumerated type that currently states active and empty. And underneath the hood, what that means is 0 is active and 1 is empty. And later we're going to add a second element called deleted. So what's going to happen is I'm going to say if its cur state does not equal empty, if cur state is active. So let me go all the way back down here. So if we say cur dot state, I should say if cur dot state equals active. So then now we're going to insert using the insert method that we wrote last lecture. And remember, because we're passing things with const and a template and a call by reference, we can instantiate a standard pair using the brackets without having to create an intermediate variable. So here's how we're going to do this. We're going to say insert, and it's lowercase I. And we're going to say old array. We're going to say cur dot key, and that gives us the input into the for the key. And then we're going to say cur dot value. And then the way you do the standard pair template as a review, you put the brackets around it. And so that creates a standard pair with a key and a value with that current value. And so we can iterate through with this insert, and that will allow us to be able to reinsert the values from the old array into the new array. Okay, does that make sense so far? So we're iterating through, and then we rehash as we encounter them in the underlying dynamic array. And once you have that, that's it. That is the full process for rehashing. So let me zoom out just a little so those of you who might have missed something can go back through. So to reiterate, we copy the current array, then we clear out the array we want to save, that's just the private member of the hash table class. Then we resize it to the next largest prime number. Then we are going to iterate through the old array. We say if it's active, we insert. And if you recall, insert increments numhash, right? Yeah, numhash. So that's going to call it for us. So now what we don't need to do, we don't need to rewrite the insert method. We were able to just call numhash and make it simple. Yes. Array is the private member of the hash table. So if we go all the way up here, that is the actual underlying array. Okay, that answered your question? All right, let me check. Okay, so I don't see any questions in the Slack. Does anybody have any questions about this before I continue? All right, so you can now save it and upload it to the Notre Dame machines. Going through that, there's the whole thing. So if you want to review that, and this is everything that I just went over. And then in insert, this is kind of a new method that I'm going to show you. It's modified in this version, but we're just going to follow along together. So there's rehash and insert. Okay, so here's how I've accounted for this. I can use that brackets for standard pair because it's const and called by reference. And so then here we have another insert and exceeds the hash capacity, we may call rehash. We always want to increment numhash, And then what's going to happen is we call that find position function method that we wrote last lecture. And that allows us to get the location. And then I'm going to create a temporary hash entry. And then I'm going to set that location from find position to the entry. So now that will update our hash table. That's everything there. And then I set that to active because we want to indicate that it's active. In the friend operator, I've made a small modification that when it prints out, it's going to tell me all of the elements in the hash table, and it's going to say whether it's active or empty. And if it's active, it's going to print out the value. So it's going to have the key and the value, and it'll print everything else out. So here I have several elements. It's going to be make LP test 6. And here I have data structures hash table lecture as a string and several integers. And then I have an int for int hash with several doubles as the value. So that's what's going to come out here. Let me run that for you. I'm going to run make LP test 6 if I did everything right. And there it is. And so now what we've done is we have said that if it's empty, it doesn't have a corresponding key. So we know the bucket number, we know the key, and we know the value. So the key was data, and the value is 22. The key is hash, and it hashed to the 5th bucket, and the value is 9. Does everybody see that? If you don't, it's perfectly fine. Please feel free to ask. I want to make sure that everybody understands all the machinations of the hash table. All right, let me go to the chat to make sure. Nothing in the chat either. Okay. And then you'll see problem3.txt up there once you have that done as well. Okay, so what I would like to do next is I'd like to bring up a small problem with hash tables and how we're going to get around it. So we've done stuff with insertion, we've done stuff with rehashing, so we can allocate a certain amount of memory. For those of you who took the lab yesterday, you learned how you can pre-process using a sizing. And for those of you who are going to take the lab today, you'll learn this today, that we can rehash in order to prevent excessive rehashing. That can get around the big O of n worst case scenario. So we have another problem with deletion. So let's say I want to delete okay, so there 48 was in there. And so what's going to happen is I removed 48 from the hash table. And what happened is it would go to 2. That location was at 2. Our linear probe algorithm would stop because it would be like, all right, it's empty. That means that I can't find this value. 55 was never inserted. So as a result, we cannot just remove elements from a hash table because any linear probing, we're going to be learning about quadratic probing on Thursday. We're going to be learning about Robin Hood hashing and cuckoo hashing. All of these are dependent upon the idea that the previous values that we used, that we had to go past to get to that location are still there. Because the algorithm stops the moment we either find the value we're looking for or it stops when we find an empty bucket. And when we delete something, it then becomes an empty bucket. So how do we get around this problem? We get around this, and I don't find it, by doing something called lazy deletion. The idea of lazy deletion is that we leave it in the hash table. So 48 is left in the hash table. However, we are going to say, instead of being active or empty, we are now going to add a third element called deleted. And we're going to just mark it as deleted. So we're going to say, oh, it's deleted, but that means that I want to still continue in my probing algorithm because at some point when I inserted 55, it was relying upon 48 being in there. So if 48 is still there and it's just marked as deleted, our algorithm is going to continue. Does that make sense? So we are going to make some modifications to our hash table to get this result. So now we say, oh, it's deleted, but that we still want to look. And then our next step takes us to 55. Let's get past that. Yeah, I left those slides in, my apologies. All right, so now I want you to go to linear probe 7.h. And first I want you to go to line 7. And at line 7, that's where we're going to have that enumerated type. So I just want to review enumerated types again, just so everybody understands what's actually going on here. What's going on here at now line 8 is that I have created a new variable called entry state. And the way that a C++ programmer would access the values would say active or empty. But underneath the hood, what's actually going on there is that means 0 and 1. So it's just like a pound-defined compiler directive. We are going to modify this to do 0, 1, and 2. And we're going to modify this by saying comma deleted. And we can see that it brought up deleted in that level. And I see there's a question in the Slack. I'll get to in a split second. It brought up deleted because I used deleted throughout the rest of the file. This allows us to now say there's 3 different ways we can represent a hash table state, a hash entry state. It can either be active. We have a value that we can consider a valid piece of data. It's empty, meaning that there's nothing in this bucket. And when we do linear probing algorithms, we would stop because there's nothing else to find, or we're going to mark it as deleted. The other good thing is if we hash to that bucket and it's marked as deleted, we're just going to overwrite it with the new value and then mark that as active. So that way our linear probing algorithms will be preserved, but we won't unintentionally lose that data. So the question in the Slack is, when we rehash, can we actually delete all the values marked as deleted? Very good question. The answer is yes. When we rehash, we have a new bucket, which means we have a new number of buckets. We have a new number of buckets, which means we have a new hash table algorithm, which means it's dependent upon those other elements. So what we can do is when we go through, we just look at active values, and we don't have to worry about deleted anymore, because when we hash it, we just don't put it in there, and then it will only be active. So Stephen, did that address your question? I gotta make sure everyone's on mute. Right. Glad to hear it, Stephen. All right, so that's the first part. So the next part of what I'd like you to do, so there's the enumerated type, is go to line 117. At least I hope I didn't give you all the wrong line. Nope, that was hash table. What I would like you to do instead is I would like you to go to line 169. So we're actually going to write a remove method. And what we're going to do in this remove method is we're actually going to use everything that we've written so far to take advantage and actually do lazy deletion. So the first thing we're going to do is we're going to find the position of the current key. So remember that memory is a long unsigned int, and we're just going to call this current position. Let me zoom out just a little so it's a little more visible. And that we're going to call that function that we wrote, that method that we wrote last lecture, find position, find POS, and we are going to pass the key. Right? The next thing we're going to do is we're going to say if it's not in the active, it's not active, we're going to say that we can't delete an element because it's not active. It's either empty or it's already deleted. So we can't delete it. So the way we're going to do that is we're going to say if the current position, and this is going to be if array dot at current position dot state is not active, then we can just return false, because this remove method returns a bool. So I want to tell the user, and this is often, and we're going to see examples of this a little later, this is often used for security. You can say, all right, if I can't delete this, then something else. So it becomes very useful to the programmer to have that Boolean used. So we now say that this is not a valid hash table. Let me say not a valid hash at key. But now if we get past that, then we can just do some lazy deletion. We can say array dot at current position dot state equals deleted. And that's it. The element's still in there, but we've marked it now as deleted. And then the last thing I want to do is I'm going to decrement the number of elements in the hash. And so we rehash when we have a certain number of active buckets. If I'm at 7, for example, and I'm at 4, but I have one that's marked as deleted, it turns out I only have 3. So then I would want to overwrite it and then consider whether or not to rehash. So here, what I'm going to do is I'm going to say minus minus numhash. And then we return true because we were able to successfully mark an element in the hash table as deleted. And so you can save and update that. What I'm going to do, I'm going to leave this up here for a moment, so if those of you who are a little behind can continue to type. What I'm not going to show you next is I'm going to go back to that find position, and I'm going to show you how I modified things by accounting for the deletion. Does anybody have any questions, or is anybody still typing this rehash? All right, so I see there's a question being typed in the chat. I'm going to go up, and then I'm going to address the question. All right, so there's next prime is prime. I'll find it. Hash function. All right, so quick note. In the coding challenge for the quick sort, I only have one hash function, and the reason why is because in the coding challenge, I'm only going to ask you to sort integers, but I have it templated so that way you could take that algorithm and go elsewhere. If in the event you wanted to use quick sort to sort anything else, you would have to write another version of that hash function in order to get the appropriate location. And that's a question I've gotten a couple of times. So for find position, there we go. Same thing, current position, iteration, step size. I get the current position and then iterate. So I do the do while. And the only thing I've added is while the array is not empty and while the array is not deleted. So once I find a deleted element, I now need to consider whether or not I want to write to that position or not. So it's not empty and it's not deleted and we haven't found the key and we haven't reached the array's capacity. Everything else is the same. And then what happens when we update it and run make LP test 7. Did I spell deleted wrong? D-E-L-E-T-E-D? I might have. Linear probe 7. Oh, there it is. Oh, I should probably run make clean. What did I do wrong? 100, 203. Unused parameter, the key. That's not true. Any theories? Anybody can see what I might have done wrong here? And enumerated type, so that's linear probe 7. Let me open up LP. Oh, that's why I didn't press yes. That's probably somebody in the chat might have pointed that out. Are you still in the include folder? And so, William, I did see your question. I'm going to address it in a moment. LP test 7. And now it compiles. So I didn't update my code, and it didn't compile because I didn't tell it what deleted meant. And so when you have that, type ls, and you will now see prob4.txt. And so the question in the Slack is, how is numhash available in every function? Because it is private. So this is in the coding challenge 5. Oh, I'm sorry, numhash is available in every function for the hash table because numhash is a private member of the class. So let me go down. We have the struct, we have these two values. So this is the vector containing all the underlying elements. And then I have the private member unsigned int num hash to indicate the number of elements that I've currently hashed. And the reason why I want to keep track of that, just to review, is because I have a capacity for the vector, but since we're not inserting them in order, I have to have another way of knowing how many valid active buckets are in that array. And so I keep track of that with an unsigned integer num hash. So William, did that address your question? Awesome. All right, so we might have another comment in the chat. Okay, good. So then everything here, I show what's going on for those of you who might want to review later. And then I go through, and now I can say active or deleted when I print everything out. So what happens here is we see that before I hashed, hash table size is 4. I'm sorry, it's 11, prime number. I've hashed 4 elements. I deleted lecture. And then we see that in that bucket, if I go down here at bucket 7, it has example. And so what I did is I overwrote a deleted element in the hash table and then was able to hash another element. So I did the same thing here at bucket 5. I have 5 as the key and 3.14 is the value. I then hashed again, and we see that I overwrote that with 5 and 28.2. Okay, so the next method that I have is called contains. For those of you who might be familiar with standard unordered map, in the C++11 library that's installed on the Notre Dame machines, that library does not have contains. We won't have a contains method until we get to C++ 2020, which has unfortunately been delayed due to the global pandemic. So the question is, how do you do that? In the lab and in the coding challenge, you saw that we use this count method, where it counts the number of versions of that specific key. Here, what we're going to do is we are going to say, all right, I want to determine whether or not this is actually in there. So in linearprobe.h, I have this piece of code that passes a const key with a call by reference. I call that find position. First, I say if that current position is equal to the array capacity. You may recall from, well, actually I just discussed it a moment ago, but in more detail last Thursday, that if I go through the entire array and don't find anything, I want to return the length of the array. And this is a great example. I've gone through the entire array here and didn't find anything. So therefore, if the current position is equal to capacity, I return false. I know it's not there. I've literally looked everywhere I can possibly look. Otherwise, what I'm going to do is I'm going to get the hash entry at that specific location. And I'm doing this, otherwise I'd have to call array.at_current_position.key.state. So this is to simplify for student understanding. I get the key, I get the hash entry at that specific location, and if the key is equal to the key that I'm looking for, and this state is equal to active. So if I have a hash table with 7 elements, I can get 11, will hash to 4, and I can get 18, will also hash to 4 initially. So that's why I first have to check if the key is equal to the key I'm actually looking up. And the second value, it has to be active because we can potentially have this lazy deletion. So that's why we have those two particular Booleans. Does anybody have any questions about that? Okay, so then what I do is I've now written array operators. So what I would like to do is I'm going to open up linearprobe.h and zoom in to these operators. And what this allows me to do is it allows me to actually access the specific location. So here's the first one. And the first one is this operator allows me to call it just like I'm treating it like an array. So when we do standard unordered map and you can use the array operator there, we're now doing the same thing with the overloaded operator. And I'm returning a reference to the value. You know, in a normal array where you have array I is equal to 10, let's say an array is an integer array. What's actually happening there in C++ is we're treating the value as an object. And when we call it by reference, all we're doing is doing a pointer. And the benefit is that for this array operator, I can change it if I want. So I can call that and update that specific value. So I bring in the value. So I bring in the key. I find the position of the key. And I'm going to explain all this in a moment. And then I return the value at that specific key's location. And I call by reference. If I want to update that, that allows me to do so. The second thing, and again, I'm going to go back to that if statement in a moment, is, well, what happens if I'm doing const? I can return the value, and if the value is a very large templated type, I'm still only passing a pointer. But if I do it by const, I can ensure that if it's a const object, for example, let's say I'm printing everything out. I'm putting it to a function that prints out the values in the hash, and I pass it with a call by reference and const. Therefore, I can do this. It's a different version, even though inside the code, it's the exact same thing. Does anybody have any questions about that? So I can do const return value and a const version of the hash table. So the last thing I want to do is I want to discuss this if statement. So how many of you are familiar with, and this is in several programming language, what's something known as an exception? Okay, so I see a few hands up. How many of you in Windows are familiar with the blue screen of death? Okay, so a lot more of you. So what the blue screen of death is a program went wrong, and the whole idea is that I indicate that I can no longer guarantee effective operation of this program. And so it throws what's known as an exception. I have an example here in code. And when it throws the exception, it does something called try and catch. A try-catch block means that I try this piece of code, and if it throws an exception, I catch it. And then when I catch it, I do something with it. What the blue screen of death is it's a thrown exception that never gets caught until it gets to the operating system level and it says, I've tried catching this with everything else. This exception is so bad that the only way I can remedy the problem is to shut the computer down entirely. Does that make sense? So what I'm going to do here is I'm going to say, all right, I am going to try to put in a try-catch block with hash tables. And one of the reasons I want to do this is because when you use standard unordered map, if you try to hash and look up using contains or using the array operators, and you try putting it in that way and it's not there, standard unordered map is going to put it in there for you. And that might not be something you want. Sometimes that's actually really bad for your operation. So what we're going to do here is I'm going to say, all right, if temp key is not equal to the key and temp state is not equal to active, what I'm going to say is I'm going to throw a standard out of range. For those of you who have done vectors, you're probably familiar with that. If you've gone outside the range of the vector, standard out of range, what that's saying is you have gone outside of the range of the vector. What's over here in the data heap does not belong to the vector, and that could be anything. That could be all kinds of gibberish. So what I'm going to do is I'm going to throw this exception, stop the program, and that way you can figure out what happened there. And so this is just a thing that will print out when we throw. And the way we do that, I'm going to scroll up to the top of the file really quick. We have to pound include std exception in order to run those exceptions. Okay, so there's the exceptions. And so what I'm going to do is I'm going to deliberately call an element 9 in LP test.8 that is not in the hash table. And so we see here that I'm calling the array operator int hash 9. So let me open up that file and show you what's going on there. In this file, I've hashed 5, 2, 7, and 1. I've removed 5, and then I try using the array operator to say, well, what's going on there? And so that should return the value. And so for example, up here, element at example, string hash example, should return 211 because that's the value that I've used with example for the key. So now what's going to happen is I'm going to try to call that, and instead of trying to just hash 9 and inserting the default constructor as the value, I'm going to throw an exception. So I'm going to run make LP test 8. And we're going to see that everything works. And at the end, it says terminate after throwing an instance of standard out of range. So our exception worked. And so now what's going to happen in the last linear probe test is now I'm going to do something with that try catch. What's actually happened here is it core dumped. It threw everything out of the memory entirely. It's like, oh, you did something outside of your range. You can't guarantee this program works. Bye, Felicia. I don't want you in my data heap or instruction stack. And that's the same thing as the blue screen of death. So now, how do we get around this? How can we actually continue to run the program? That's where the last thing for lptest.cpp comes in. And what I've done here is I've written this function access operator example. So I have a const hash table, the hash, and key lookup. And I am going to call this function for every single key. And what's going to happen here is if it's there, all it's going to do is it's just going to print the element at the lookup, key lookup is the value when I call the operator. If it doesn't work, I'm just going to say attempted lookup with key, and I'm going to see out the exception dot what, right? And all that's just going to do is going to say that it's not there, but because I have caught it, we're going to continue the program because I now say, if it doesn't work, we're just going to print an element to the user every time. And that's going to make it work. So if I run make LP test at the end, we're going to see that it's going to continue. And what it does is attempted lookup with key 9, hash table does not contain the requested key. So when I call dot what that actually does is it goes into the class where we threw the exception and it includes that message. And if we recall from linear probe, when I go down here, the message that I included was hash table does not contain the requested key. And that is precisely what is printed. And so the benefit of this is actually the next operation. I go past that, I now know that 9 is not in there, I've protected my program. The program can still operate, and I can still now look up if 7 is in the hash, and we see that it is active and negative 22.6. And so by doing this, I am not unintentionally adding more elements to the hash table. So this is a potential solution if you don't like standard unordered map. And I can continue the operation of the program. And ultimately, whichever you choose to use is up to you in your environment. Does anybody have any questions about that? Okay. Is everything there? All right, so what I would like to do for the rest of the lecture here is I want to talk about priority queues. So you did your first crack at a priority queue in Coding Challenge 4. You used a doubly linked list, you wrote a sort method, and then when we sorted it, the element that we wanted at the top, at the front of the doubly linked list was the largest element. All of the elements in that doubly linked list were sorted. So there are some pros and cons to this. The pros are, it's automatically sorted. Once I'm done, I can get all the elements in there. However, there's a drawback, and the drawback is that insertion in the worst case scenario is big O of n squared time. I presented that to you. Remember that proof with the Taylor series that I presented a couple of lectures ago? Yep. That's the exact same proof for the insertion into the doubly linked list. So it's big O of n squared. So the question is, can we beat that, and what's it going to cost me to do that? And so we're going to introduce a new data structure now called a heap. And the heap is actually something that resembles what we're going to call a binary tree, in that we have one value. The first value there is 81, and it's going to have what we're going to refer to as children. And its two children in this heap are 27 and 33. And 27's children are 21 and 1, and 33's child is 7. And what we're going to say about a maximum heap is that its property is that neither child is greater than the parent. Neither child is greater than the parent. However, we're going to notice that it's not sorted. It's heapified. So the term heapified means that the higher you go up in the heap, the larger the value. And our goal is to have the largest value at any given moment at the top of the heap. And that is called a maximum heap. And so let me go through a process of what we're going to do. If I want to insert 44, what we're going to do is we are initially going to put 44 at the next available location, which would be here, because a heap is what we're going to call a complete tree. There's no empty locations. And when we study binary search trees, and we get into AVL trees and splay trees and red-black trees and B trees, we're going to discover that this notion of an incomplete tree is a real problem. And we are going to address this now by saying, first thing I'm going to do is I'm going to insert at the location to keep it as a complete tree. Does everybody see that? All right, so then what's going to happen next is I want to do this heapification. So I'm going to compare the value I just inserted and its parent. 33 is less than 44, and I'm going to swap them. The reason I can do this is because if 33 is here, whatever its children are down there must be less than 33. And so any value that's greater than 33 must also be greater than whatever is below 33 in the heap. Does that make sense? That's a crucial property to this data structure. So now I swap 33 and 44. And so how did the origin of max heaps come about? So max heaps were invented, I believe in 1964 by J.W.J. Williams, and he was working at what is now Raytheon. And like many of you in here, he really, really hated pointers, could not stand them. And he's like, is there a way in which we can get big O of n log n search without having to deal with all these pesky pointers? And what he came up with was the heap. And it solved a specific task, which is how can we come up with a faster way of inserting and finding elements into a priority queue? And so what's actually going on is we are using a max heap, but the underlying data structure, just like a hash table, is a dynamic array. And we can grow it, and then we're just going to use mathematical representations between what we expect the parent to be and what we expect the child to be. And so here, what I have is the representation of the max heap, but if I go through 1, 2, 3, 4, 5, in this particular order, we're going to learn that's called eventually when we get into trees, we're going to call that level sort order. And we're actually going to figure that out using that breadth first search algorithm that I showed you with queues. So all of these pieces are going to start coming together later in the semester. Well, what's going to happen is the parents, if the value is even, the specific location. Let's say 2, right? 44 is 2. And so therefore, 2 divided by 2 is 1, and 1 minus 1 is 0. So 44's parent is 81. Does everybody see that? Same thing here, if it's even, so let's pick 0, 1, 2, 3, 4. Let's pick 7, right? 7 is 5. Okay, I just got paranoid there. So 5 divided by 2 is going to be 2. We don't subtract 1, which means that the second location as parent is 44. And so we use that mathematical representation to figure out where the parent is. And so we can use that to heapify elements up the tree. I'm sorry, up the heap. Does that make sense so far? Okay, next thing, to find a child, let's say we are at 0, we're at 81. 0 times 2 plus 1 is going to be the child, so 0 and 1. This should be plus 2, my apologies, I'll fix that in the slides. Plus 2 becomes 44. So 44 is 2. 2 times 2 plus 1 is 5. 2 times 2 plus 2 is 6. And so this is where we correlate these values. Does that make sense? And so we're going to use those mathematical relationships to be able to determine what a maximum heap is. Oh, so one quick thing. If you're ever on the second floor of Fitzpatrick Hall, there's this huge stained glass window. And the stained glass window contains representations with different images from all the different majors in the College of Engineering. And one of the images that they have on there is this, which is actually a maximum heap. So the representation for computer science is what we're studying today. So that's what's up there in the glass. If you ever want to look at that, that's a maximum heap. So what we're going to do is I'm going to walk through this process, and I want to show you how it's actually working at multiple levels of abstraction. On the left, this heap representation is the algorithmic level of abstraction. But now we're getting to the procedural level of abstraction, which is the array. And so the way this is going to work is we want to insert 44 like we did before. What's going to happen is we're first going to push back onto the vector, and that element is now going to be there. And then we're going to use that mathematical representation to determine what these values should be. So what's going to happen is I'm going to use parent 6 is an even value. So 6 divided by 2 is 3, minus 1 is 2. So the parent is currently 33. Since 44 is greater than 33 in a maximum heap, I swap them. And I continue that process until I either find a value that's bigger or I reach the top of the heap. So the next element, what I'm going to do was I would compare 44 and 81. So it would be 2 divided by 2 is 1, minus 1 is 0. And 81 is bigger than 44, so we terminate. So now what I'm going to do is with this hash, I'm going to insert 2 more elements, 0 and 99. These two, because we're going into the next row, this should hopefully clarify some of the one of the issues with this idea of a complete binary tree. So when I put in 0, at the algorithmic level on the left, I'm just putting it as a child of 21 initially. At the procedural level, we see that I've pushed 0 back onto the dynamic array. 0 is greater than 20, I'm sorry, 21 is greater than 0, so we stop. Next, I put 99. So do you see that we're now starting to fill in? We filled in 44, we heapified, so 33 is at that complete binary tree location. Then we had 0, now we've pushed 99 back, and now we're going to heapify this. So 99, we see that it's 8 divided by 2, which is 4. 4 minus 1 is 3. That gives us 21. 99 is greater than 21, and we swap. The next thing, now we're at 3. 3 divided by 2 is 1 since it's odd. 27, we swap those. And then 81 and 99. 99 is greater than 81. And now we have the top element in the top of the binary heap. Does that make sense? Okay, so now we can only access the top element like a priority queue. So what you did in coding challenge 4 is you deleted all the elements in order to get that sorted result, right? So now, if we remove an element from the heap, we have to figure out how to ensure that after we pop it off, how is it that we're going to ensure that the biggest element is there? So one of the biggest elements is going to be here. But there's no guarantee. A valid, so let me give you an example. A valid heap would be if this was 44 and this was 81, which means this would be 44 and this would be 81. So we can't just use the next element. So we have to come up with a process to do so. And I see there's a question being typed in the Slack. I'll address it when it's ready. So the first thing we're going to do is we are going to swap the elements in the beginning and the end of the dynamic array. So it's going to look like this. I'm going to swap 21 and 99. They get swapped. So now 29 is now at the end. 99 is now at the end. And then I'm just going to delete the last element in the dynamic array. So now that's gone. It's out of the heap. So now what we need to do is we need to find 21's rightful new place in the heap. So what's going to happen is it has 2 children. And so now we're going to use that parent to child relationship, 2 times the value plus 1 and 2 times the value plus 2. And then what we're going to do is we're going to take the larger of the 2 values and we're going to swap. So here in this case, we're going to swap 21 and 81. So that means that 81 is now going to be moved up, and 44 is smaller than 81, but now 21 is swapped down here. The next thing we're going to do is we're going to keep checking on 21 until it's in the right place. So 21, we're going to compare those 2 children, and we're going to take the larger of those 2 values. In this case, it's 27. 27 gets moved up. 27 is now bigger than 21 and 1, so it's valid. And then we compare 21 and 0. What we're now going to do is we are going to say, well, 0 is less than 21. We are done. All right, so I'm going to pop again after I address the question in the Slack. When adding 99, could we place it under 1, or does it have to go under 21? It must go under 21 in order to maintain the complete binary tree property. That is its initial location. It must go there because that's the end of the underlying dynamic array. And so what is the formula for comparing a parent to its child? So this is a few slides back. Let me show you again. So this was, I don't have to go back. I'll just repeat. So, okay, so we're going to get 21. We swap here. We go all the way down. And so the parent here, it's parent times 2 minus 1, and plus 1 is the left child. So if this was 27, it's 1. 1 times 2 is 2, plus 1 is 3. We see that 3 is 21, which is here. And 1 times 2 plus 2 is this location there. All right, so now we're going to pop again. So Selena and Nikita, please let me know if that has addressed your question. So we're going to remove 81. And the way we're going to do it again is we're going to swap 81 and 0. And then we're going to remove 81 from the dynamic array. And then we are going to pick the 2 children. 44 is bigger than 27. So we swap. And then we go to the next place for 0. 33 is greater than 7, so we move that up. Then one more time, we're going to remove 44. We swap. We remove 44. 33 is greater than 27, so we swap there. It only has a left child, so we are going to swap. 7 moves up, 0 goes down, and that is our priority queue. And so what I would like you to do before I show you some code is I want you to work on problem 5. Problem 5 goes through the whole process of inserting and deleting. So let me run make problem 5 here. And so you're going to insert 33, 21, 81, 27, 1, 7, 0, 44, 0, and 99. And then you're going to remove the top 2 elements. And then the solution to this problem, as you would see on an exam, is the underlying dynamic array, just like I presented in the slide. So please take a couple of minutes to work through, and then we'll work through it together. And we continue to, I'm going to answer a question in the Slack while you're working. The question in the Slack is, how would starting from an empty tree work? So I'm going to show you in code in a little bit, but generally, we start with an empty dynamic array, and then when you get the first element, you just hash it. You just put it in there. It's not a hash. You put it in there, and it's just a dynamic array of length 1. So if it's, in this case, it's 33, so 31, so the first one will always be 31. Okay. So Sebastian, let me know if that addressed your question. All right, good. Okay, so first, who can give me the correct selection for the solution? Who wants to tell me the correct answer? Whole classroom full of shy people, maybe tired people. Yes. B? All right, so I believe B is the correct answer. I see there's a couple more who are going in there, and B is in fact the correct answer. So for those of you who are typing that up, you're probably getting it right. So let me walk through real quick and show you why it's B. So when I would approach something like this, 31 and 21, I look at these 2 first. So this is 41. I would actually, I gotta mute everybody here, mute all. No. I would actually start out and do 41 and then 31, just to make things a little easier. You'll see that in the videos that I have on the exam review. But it'll be 31, 21, 81 is going to be swapped with 31. And the reason why is because 81 initially goes there. Then we have 27. 27 goes up here, and 21 moves down here. Then 1 has its valid location there. Then we have 7, 44 would go here, so I'd move 44 there and put 31 here. Then I have 0, and then if it was 99, I would move everything up. So this would become 21, 27, 81, and this would become 99. I would pop the first element off, which would be 99. So the way to do that would be to move 21 up here. And then what's going to happen is, this is 81. 81's bigger than 44. And 44 is bigger than 27 and 1. I hope I have that right. Did I screw up there? It's going to be 31 and 44. All right, so now we pop off the second element, and we're going to have 81 there. 81 gets swapped with the last element, which is 0. And then we see which one is bigger. And that gives us 44. And then it would be 0 here because we would be putting 27. Okay. Okay, we have a comment in the chat. B. All right, yes, Marcelo, that is correct. B is the correct answer. Very good. Okay, so the next thing I want to do is we're going to do 2 thought questions together. So first thing I want you to do is I want you to make run prob 6, and it's going to give you a multiple choice question with multiple answers. And Elijah, I'll get to your question in a second. I was probably drawing it fast, but 1 would go here. Oh, that's a good point. I'll get that fixed. So 1 is where I drew it out. So here what the question states, what are the primary benefits of using a max heap for a priority queue instead of a sorted doubly linked list? There are 2 correct answers. So let's think about each one and which one is a benefit. So insertion time of big O log of n for each element. Is that a benefit for a max heap, yes or no? So we're going to say yes, so A is one of the right answers. Guaranteed big O1 removal for all elements. Is that true? For a max heap? No, I'm seeing a bunch of shaking heads. No, that's correct, because we have to propagate through, so we have a worst case big O log of n. So C, aggregating a dynamic array instead of using pointers reduces memory if the templated type of the priority queue is large. So I'm going to go to the students who had the lab yesterday. So I had that chart comparing vectors and linked lists. So if it gets bigger, which one is better, the linked list or the dynamic array? Remember from that chart? Yes. Very good. Linked list is correct. So this is not a correct answer. So by process of elimination, we know this is D. Use of balancing mechanisms instead of sorting reduces the need for exact sorting after every push or pop. And this is the primary main benefit of a max heap. So A and D is correct. And now I want you to do prob 7, and it's just the opposite of what are the benefits of doubly linked list. So the benefits are B and C, which is that guaranteed big O1 removal for all elements. So if we do a lot of pre-processing, worst case scenario is big O of n squared, but then we get big O of 1 on the back end. So that is a benefit. And then, as we've just discussed, if the template type gets bigger, the use of a dynamic array goes away. So the bigger the templated type is, the more that we might want to choose a linked list. So in this case, B and C is the correct answer. And so from there, if you have it all done, you'll see that prob 1 through prob 7 is complete. And if you run test.n, hide. Okay. But yeah, if you have prob 1 through prob 7, you will get full credit. The last thing I'm going to show you, so I'm going to start showing you now, but we're going to build up towards the design of a max heap, is that we use the underlying vector, and then for the constructor, we just create it, so it answers that question from a little earlier. It just starts at 0. I will go into this much more detail because we have 10 seconds left in the lecture. at the beginning of Thursday's lecture, but the general idea is we're going to go through that algorithm for push and pop and show you simply how it is that we use it for maximum heap. So if you have Prob 1 through Prob 7, the TA grading it will see everything and give you full credit for the assignment. And on that note, if there are no other questions, you are dismissed.